Good morning, welcome to Currents Convert. In this video, let us study ATROPISOMERISM. It is also called axial chirality. Axial chirality, we will see in detail. Okay, why do ATROPISOMERISm occur? Let us consider biphenyl compound or biaryl compound. Okay, there are two phenyl rings as you see here. One is in the plane, this is perpendicular to this. Okay, this wedged means it is pointing towards us. Okay, on rotation, what happened? There is a free rotation at this carbon-carbon single bond, sigma bond. Therefore, both will become this is also perpendicular. Okay, and then if you rotate this will become parallel to the parallel. This is perpendicular. Okay, so biphenyl compounds or biaryl or compounds where two phenyl or two aryl rings are connected by a central sigma bond. In unsubstituted, for example, in this case unsubstituted. In unsubstituted biphenyl, there is sufficient amount of free rotation around the central sigma bond. There is freedom of rotation. There is free rotation about this carbon-carbon sigma bond. Hence, there is free interconversion between rotamers, conformers, so that they do not exist independently, they cannot be isolated because of free rotation. Okay, now let us introduce substituents, bulky substituents at the ortho positions of each biphenyl ring. Now what will happen? Because of the bulky groups, substituents, there is steric hindrance. As a result, the free rotation is hindered. The free rotation, there is no free rotation. As a result of absence of free rotation, that is axial, that is why it is called axial chirality. Okay, and it exists in two different isomers, conformers, rotamers, stereoisomers, whatever you call. Okay, they are called. Okay, however, biphenyls with large substituents at the ortho positions on either side of the central sigma bond experience restricted hindered rotation along this bond due to steric hindrance. So the free energy barrier to rotation is very high. Therefore, there is no free rotation. If the substituents are different, you see here, the substituents are different, nitro group, carboxylic acid group, then it will become a chiral molecule exhibiting a pair of enantiomers called ATROPISOMERS are formed. Okay, here there are two enantiomers, 6,6 here, 1, 2, 3, 4, 5, 6. Therefore, 6,6 prime dinitro biphenyl 2. This is 1, 2, 2 prime dicarboxylic acid. There are two enantiomers due to ATROPISOMERISm. Okay. Similarly, binaphthol. This is naphthol. This is another naphthol. Therefore, binaphthol, polynuclear aromatic systems also exhibit enantiomerism. You see here, it's this is the object, this is the mirror image. There is a mirror plane. Okay, so you have the optical rotation, specific rotation is plus 35.5. It rotates the plane polarized light towards left minus 35.5. So what are the important features of ATROPISOMERISm? They are stereoisomers arising due to restricted hindered rotation about a carbon-carbon sigma bond. In Greek, A means not, tropos means turn, not able to turn, not able to rotate. As a result, the isomers are obtained called ATROPISOMERS. Bulky substituents on ortho positions may enhance the energy barrier to rotation, so there is no free rotation. As a result, there are two distinct enantiomers, stereoisomers, conformers, rotamers are formed called ATROPISOMERS. This phenomenon is called ATROPISOMERISM. ATROPISOMERISM is also called axial chirality. For example, in tartaric acid, they have plane of symmetry, they do not have plane of symmetry. As a result, they exhibit optical activity. Here, it lacks axial symmetry. Okay, so it is called axial chirality. So ATROPISOMERISM is also called axial chirality. The chirality is not simply due to point or plane, but due to an axis. So it is called axial chiral molecule. Thank you for watching. Please share and subscribe. Thank you again.